So what we are looking at is the user interface of Turbo Design 1, which is the 3D inverse design code, and we will use it to design the inducer and impeller for the turbopump for 3 different configurations. So the first configuration, which is a separate inducer with a secondary impeller, and let me start by opening the inducer input file, which was exported from the mainline code TD-pre. As you can see, all these specifications here, like the flow rate, RPM, etc., have already been filled in from the TD-pre file, and we can also see the meridional shape, which again comes from the mainline code, along with this 2D grid, which is automatically created and can be adjusted using these options here. And the solver is actually a 3D code, and even though we don't have a numerical grid in the tangential or the pitchwise direction, it solves the equations using discrete Fourier transforms, and that's why the code is very fast and is numerically quite efficient. Now, we support different type of thicknesses such as normal and tangential, and in terms of type, we have a simple constant thickness as well as more complex distributions like the Naka profile and the flexible control points. But in this case, we can go with the typical flat plate type constant thickness. And actually this possibility to specify thickness as part of the inverse design is very useful because it guarantees structural integrity. And if you have some existing thickness profile, then you can also import that using this option here. Now, blockage is something that we use only for cases with significant boundary layer blockage, such as transonic flows, and so we can skip that for now. And then we specify some fluid dynamic inputs, which is the blade loading, and this is the most important parameter for the inverse design method. And here we first specify the span-wise RVT star, which is the swirl distribution from the hub to tip. So here 0 span-wise location is the hub and 1 is the tip. And then we are imposing the span-wise swirl distribution at the leading and the trailing edge of the blade row. And the distribution is free vortex, so there is 0 swirl at the inlet, meaning a purely axial flow, and then a constant value from hub to shroud at the outlet. And if you recall the Euler turbomachinery equation, then the difference in RVT star between the inlet and the exit gives you the specific work of the blade row. And this is important because it means that every design coming out of TD1 respects your required duty point. And now that the overall blade work is fixed, we need to specify how it varies from the leading edge to trailing edge at the hub and the shroud sections. And for this we have the streamwise blade loading, which directly controls the blade surface pressure distribution, and this is basically the derivative of RVT star, and it directly relates to the pressure jump across the blade. So here we have this parabolic section from the leading edge to this point here that you can vary, then a linear section between these 2 points, and then from this point to the trailing edge we have another parabolic section, and then the loading at this point defines the incidence at the leading edge, and at the trailing edge the loading is always 0, which satisfies the kata condition. And so with these 4 settings you can easily parameterize the 3D blade loading for manual adjustment or for automatic optimization. And of course the distribution is uploaded in this case. And then the last important parameter is the stacking condition. And so on one quasi-orthogonal, we actually specify the variation of the wrap angle from the hub to tip, and in this way you can lean the blade, and this will create a span-wise pressure force or gradient. And this is something that you can also use to additionally influence the 3D pressure field. but for now we can continue with the zero or radial stacking at the trailing edge. Now, even though the program is fully 3D, it runs very quickly, and within 10 seconds or so it gives you the blade geometry and also quite an accurate inviscid flow information. And then this information is something that we can use to iterate on the design. So first we can take a look at the converged rotor geometry using this 3D plot here. And then we can also create 2D plots of let's say surface pressure at the hub and shroud. And in our experience, when we compare surface pressure from TD1 versus CFD, we get a very good match even though TD1 is inviscid. And that's because the viscous effects don't really impact the static pressure field, and they do distort the velocity field, but we can relate the isentropic Mach numbers and isentropic velocities to some performance parameters which we can use to explore the design space. And you can see these performance parameters here in the project manager window. Such as indicators of secondary flow, diffusion, profile and leakage loss, and geometry parameters such as throat and lean. And then under this UDP section, you can also use Python scripts to develop your own specific parameters. And finally, the selected design can be verified with a CFD and FEA analysis. And for this, the geometry can be directly exported from TD1 to different format files. That are needed for mesh generation, such as curve files for TurboGrid or step files for ANSYS Mechanical. And then we follow a similar procedure to design the impeller and import the impeller input file exported from TDPre this time. And now all the settings are updated for the impeller, so we can have a look at the meridional shape and then the thickness, which is actually NACA profile distribution in this case. And now if we come to the blade loading, we can see that the span-wise RVT star at the impeller leading edge is the same as that at the inducer trailing edge, which automatically ensures a good matching between the two components. And then the stream-wise loading is forloaded at the shroud with an aft-loaded hub to suppress the secondary flows, and we can again stick with a zero trailing edge stacking and then generate the impeller blade like this. And then just as for the inducer, we can check the 2D surface plots. And also the performance parameters. And then we can have a look at both the inducer and impeller together on a 3D plot like this. And then of course we can then finally export the impeller design for a CFD analysis.